Welcome back to the deep dive. Just take a second and think about all the electricity that's humming around you right now. Your phone charging, maybe the lights overhead, the fridge.
Absolutely. It powers basically everything in modern life. Hospitals, industries, our homes.
But we usually just, flip a switch or plug something in. We don't often stop and ask,
Yeah.
what is this stuff? How does it actually get from the power plant to my light bulb?
And that's exactly what we're diving into today. We want to get past just on or off.
Right.
We're looking at the fundamentals. What makes electricity flow? What actually is the flow? And critically, what controls it? What resists it?
Okay, so let's start with that idea of flow, electric current.
Yeah.
The sources use a great analogy like water. Water flowing in a pipe is a water current.
So electric current is just the flow of electric charge, usually electrons moving through something like a metal wire, a conductor.
And how do we measure that flow? Like how much is flowing?
We measure it as the rate of flow. So how much charge, which we call Q, passes a specific point in a certain amount of time, T. That rate, Q divided by T, is the current I.
Got it. And the unit is?
The unit is the ampere, usually shortened to amp or just A, named after André-Marie Ampère, a French scientist.
Okay. And 1 ampere is defined pretty simply.
Yeah.
It's 1 coulomb of charge moving past a point every single second, 1 coulomb per second. Now, here's something I found really surprising in the sources. The direction.
Ah, yes, the convention versus reality.
Exactly. We now know it's negatively charged electrons that are actually moving in the wire.
They drift from the negative terminal to the positive.
But the conventional direction of current, the one we draw in all our circuit diagrams,
Is taken as the direction positive charges would flow, which is opposite to the way the electrons are actually moving.
that's wild. Why stick with that?
Well, it's a historical thing. They defined the direction before they even discovered the electron or fully understood its role. So the convention stuck. We just have to remember it when looking at diagrams.
Okay, so it's like an old map that's still useful even if north is pointing down.
Something like that.
Let's make this current idea more concrete. The source had a good example, example 11.1, a simple light bulb.
Right. Say a bulb draws a current of half an amp, 0.5 A,
Okay, pretty standard. And let's say it's on for 10 minutes.
which is 600 seconds. So if you want to know the total charge that flowed through that filament,
You just multiply the current by the time, right?
Yeah.
0.5 amperes times 600 seconds.
exactly. And that gives you 300 coulombs.
Wow, 300 coulombs. That sounds like a huge amount of charge just for a light bulb for 10 minutes.
It is. It really shows you the sheer number of electrons moving, even in a simple circuit.
So we have this flow, this current,
Yeah.
but things don't just flow on their own, do they? Like water in a horizontal pipe doesn't move unless there's some pressure?
Precisely. You need a push. Water needs gravity, maybe a pump or a height difference, like a water tank up high, pushing it down.
So what's the electrical equivalent of that pressure difference?
That's what we call the potential difference, often just called voltage. We use the symbol V.
Voltage. Okay. And charges won't move in a wire without it.
Nope. They need that difference in electric pressure between 2 points in the circuit to get them going.
And where does this voltage, this push, usually come from in a simple circuit?
Typically from a battery or an electric cell, the chemical reactions happening inside the battery create and maintain this potential difference across its terminals. One end has a higher potential, the other lower.
So the battery is doing work to create this difference.
Exactly. And that leads us to the formal definition. Potential difference, V, is the work done, W, to move a unit of charge, Q, from one point to another. So V equals W divided by Q.
Work per unit charge.
Got it.
Got it. And the unit for this?
Is the volt, again, named after Alessandro Volta, another pioneer.
Right. And 1 volt means?
1 volt means that 1 joule of work is done to move 1 coulomb of charge between those 2 points. It directly connects the electrical push to actual energy expenditure.
Okay, let's use another example from the sources, 11.2, to nail this down. Say you have a 12-volt car battery,
Okay, standard car battery voltage.
and you want to know how much work, how much energy it takes to move a charge of 2 coulombs across that 12V potential difference.
Well, using the formula V equals WQ, we rearrange it to W equals V times Q.
So 12 volts times 2 coulombs.
Gives you 24 joules. It takes 24 joules of energy, provided by the battery's chemical reactions, to move those 2 coulombs of charge through the circuit connected to it.
That really clarifies it. The voltage tells you the energy punch behind each bit of charge.
And ultimately, that energy is what you pay for on your electricity bill, the work done to move all those charges.
Okay, so we have the flow, current I, and the push, potential difference V, there must be a connection, a relationship between them, right?
There absolutely is. And understanding this relationship is key to understanding pretty much all electric circuits.
It sounds like where ohm comes in.
Exactly. Georg Simon Ohm, a German physicist back in 1827, he experimented and found a fundamental relationship.
What did he find?
He discovered that for many materials, especially metals, the potential difference V across a conductor is directly proportional to the current I flowing through it.
Directly proportional. So if you double the push, you double the flow.
Yeah.
Precisely. As long as one crucial condition is met, the temperature of the conductor stays the same.
Ah, okay. Temperature matters. And this relationship, V is proportional to I. That's Ohm's law.
That's Ohm's law, usually written as V equals I times R.
Okay, V equals IR. What's the R?
R is the constant of proportionality in that equation. We call it resistance.
Resistance. So it's like friction for electricity.
That's a great way to put it. Resistance is the property of a material that resists or opposes the flow of electric charge. It hinders the movement of electrons.
That has its own unit.
It does. The ohm, named after Georg Ohm himself, the symbol is the Greek letter omega A.
So why do materials resist? Why isn't it just a smooth ride for electrons in a copper wire?
Well, the electrons aren't moving in a perfect vacuum. They're moving through a lattice of atoms within the conductor.
And as they move, they collide with these atoms or are attracted and deflected by them. This constant jostling and interaction slows them down. It retards their motion. That's the microscopic origin of resistance.
So it's like trying to run through a crowded room.
Exactly. The more crowded the room or the more obstacles, the harder it is to get through, the higher the resistance.
This resistance idea explains why different devices behave differently even on the same voltage, right? Like a feeder versus a tiny LED.
Absolutely. Let's take your standard home voltage, maybe 220 volts. A small light bulb might have a very high resistance, say 1200 ohms.
Okay, high R.
So using VIR, the current I would be V divided by R, so 220, 1200. It's a very small current, less than 0.2 amps.
Right, it doesn't need much flow.
But now think about an electric heater. Its job is to draw a lot of power to generate heat. So its resistance has to be much, much lower, maybe only 10 ohms.
Okay, low R.
So at the same 220 volts, the current I equals 220/10. That's 22 amps. A huge current compared to the bulb.
Wow, okay. So low resistance allows high current flow for the same voltage push.
Precisely. The resistance value essentially dictates how much current will flow for a given voltage.
And does this resistance, R, depend on the wire itself, like its shape or size?
It absolutely does. Experiments show three main factors control the resistance of a conductor.
Okay, what is it?
First, the length of the conductor, let's call it $. Resistance is directly proportional to length.
Makes sense. Longer path, more obstacles, more resistance.
Exactly. Double
Got it.
the length, you double the resistance, assuming everything else stays the same. Okay, factor one, length. What's next? Second, the area of cross-section, A. Think of this as how thick the wire is.
Right.
Resistance is inversely proportional to the cross-sectional area.
Inversely, so thicker wire means less resistance?
Yes. A thicker wire provides more pathways for the electrons to flow. It's like having a wider road, so easier flow, lower resistance. This is important. Thicker wires are better conductors, all else being equal.
Okay, length makes it higher, thickness makes it lower. What's the third factor?
The third factor is the nature of the material itself. Different materials just inherently resist electron flow differently.
Ah, so copper is different from rubber, obviously.
Massively different. We quantify this inherent property with something called resistivity, represented by the Greek letter rho.
Resistivity, so it's like a fundamental property of the substance.
Exactly. It tells you how strongly a material opposes electric current, independent of its shape or size. Good conductors, like silver and copper, have incredibly low resistivity. We're talking values around 10 picometers.
Tiny numbers. So they barely resist at all.
Pretty much. That's why we use them for wires. But then you look at insulators, like glass or rubber. Their resistivity is astronomical. Maybe 10, 12 tenatinometers?
Huge numbers. So they basically stop the flow completely.
For all practical purposes, yes. That's their job to insulate.
Now, the sources mentioned alloys, like nichrome used in heaters. Why use an alloy instead of a pure metal like copper? Copper's a great conductor.
Ah, but for a heater, you don't want a great conductor. You want something that gets hot, which means you need significant resistance.
Sure.
Alloys, like nichrome, which is nickel, chromium, maybe some iron, have two key advantages for heating elements. First, their resistivity is generally much higher than that of their constituent pure metals.
So they resist more and get hotter for the same current.
Right. Remember, the heating effect we'll touch on later depends on resistance. Second, and this is crucial, alloys like nichrome don't oxidize, they don't burn up easily, even when they get red hot.
Ah, durability.
Yeah.
Copper would just burn away at those temperatures.
It wouldn't last nearly as long.
Wow.
So nichrome gives you good heat generation, and it can withstand the high temperatures needed for toasters, electric irons, heaters, and so on. It's a clever materials science choice.
That makes sense. You're balancing properties. And you can even work backwards, right? Like example 11.5.
Yes. If you measure the resistance of a wire and you know its length and its cross-sectional area, you can calculate its resistivity using the formula Dopper.
So you rearrange that to find a rho.
Exactly. And if you calculate, say, $1.84 times 10⁶ ohms, you can look that value up in a table.
And it tells you the material?
That value corresponds to manganese. So the physics itself, the electrical properties, can help identify the substance.
Very cool. Okay, so we have individual components with resistance. How do we typically connect them together in circuits? There are really two fundamental ways to connect components, or resistors, in series and in parallel. Okay, series first. What does that mean?
Series means connected end to end, one after another, forming a single path for the current. Think of beads on a string.
One path. So the current.
Has to be the same through every single component in the series circuit. There's nowhere else for it to go.
Okay, same current everywhere. And the total resistance.
In series, it's simple. The total equivalent resistance, $3, is just the sum of all the individual resistances. $3 is just the sum, R1 plus R2 plus R33, and so on.
Easy enough. Add them up. But series circuits have some downsides, don't they? I'm thinking of those old Christmas lights.
Ah, yes, the classic one bulb burns out, the whole string goes dead problem. That's a major disadvantage of series. If there's a break anywhere in that single path.
The circuit is broken and nothing works.
Exactly. No current can flow at all. Nightmare fuel for finding one faulty bulb.
Tell me about it. And there's another issue, right? Something about devices needing different currents. Example 11.3 mentioned this.
Yes. Because the current is the same through everything in series, it's really impractical for connecting devices that are designed to draw very different amounts of current.
Like the heater and the light bulb example from earlier?
Precisely. A heater needs maybe 10 amps, a bulb needs maybe 0.5 amps. You absolutely cannot run them properly in series from the same voltage source because they'd be forced to have the same current, which would be wrong for both of them.
Okay, so series has its problems for practical applications like home wiring. What's the alternative?
The alternative, and the way your house is wired, is parallel.
Parallel. How does that work?
In a parallel connection, components are connected across the same 2 points in the circuit. Imagine multiple bridges crossing a river side by side. Each component provides a separate path for the current between those 2 common points.
Multiple paths. So the current splits up.
Exactly. The total current coming from the source divides itself among the different parallel branches.
And what about the voltage in parallel? This is the key difference and the main advantage.
Yeah.
The potential difference voltage across each component connected in parallel is the same.
Ah.
So every appliance plugged into your wall sockets gets the same voltage, like 220V or 120V, depending on where you are.
Precisely. That's crucial for them to operate correctly.
How do you calculate the total resistance in parallel? Is it just adding them up again?
No, it's a bit more complicated. The reciprocal of the total parallel resistance is equal to the sum of the reciprocals of the individual resistances. So 1R P equals 1R1 plus 1R2 plus 1R3 plus...
Okay, that's less intuitive. But what does it mean for the total resistance? Here's the really interesting part. When you add resistors in parallel, the total equivalent resistance of the circuit actually decreases. It's always less than the smallest individual resistance in the parallel combination. It goes down. That seems weird. You add more things, and the resistance gets lower.
Think about it like opening more checkout lanes at a supermarket. Even though you have more checkouts, resistors, you've provided more paths for the customers to flow through, so the overall bottleneck or resistance to getting through is reduced.
Okay, that makes sense. More paths mean easier flow overall.
And this is the massive advantage for domestic wiring. Each appliance operates independently at the correct voltage, and adding more appliances in parallel actually lowers the total resistance, allowing the system to draw more total current from the source as needed without affecting the other appliances.
Got it. So parallel for homes, same voltage for everything. Independent operation, lower overall resistance. You've got it. Okay, we've covered the push, V, the flow, I, the resistance, and how to connect things series parallel. But where does the energy that the battery or power source provides actually go?
That's a great question. The source is constantly doing work, expending energy to push those charges through the resistance. What happens to that energy?
Well, some might be converted into useful work, like a motor spinning a fan blade.
True. But even in a fan, not all the electrical energy becomes kinetic energy of the blades. Some energy is always lost, or rather converted, into something else.
Heat.
Heat. In any circuit with resistance, some electrical energy is inevitably converted into heat energy as the electrons collide with the atoms in the conductor. If the circuit contains only resistance, like a simple heating element, then essentially all the electrical energy supplied is dissipated as heat.
And there's a law for this heating effect, too, isn't there?
Yes, Joule's law of heating, named after James Prescott Joule.
What does it state?
It quantifies the heat produced. The heat generated, H, is directly proportional to the square of the current, I don't know dollars, the resistance R, and the time T for which the current flows. So I do dollars, I2R.
I2. So the current has a really big impact. If you double the current,
You quadruple the heat generated. That I2 factor is really significant.
and we actually use this heating effect deliberately, right?
Oh, absolutely. It's the principle behind electric heaters, toasters, ovens, electric kettles, irons, all devices designed specifically to produce heat.
Even the incandescent light bulb, the old-fashioned kind.
Yes, its primary output is actually heat. The light is almost a byproduct of the filament getting incredibly hot.
And that filament is made of tungsten. Why tungsten?
Because tungsten has an extremely high melting point, about 3,380 degrees Celsius, it needs to withstand getting white hot to produce visible light without melting.
Wow, that's hot. And they fill the bulbs with special gas, too.
Usually inactive gases like nitrogen or argon. This prevents the hot tungsten filament from reacting with oxygen, which would cause it to burn out very quickly, and helps prolong its life.
Clever. What about fuses? They use the heating effect, too, but for safety.
Exactly. A fuse is a crucial safety device. It's basically a short piece of wire made of a specific metal or alloy with a carefully chosen, relatively low melting point.
Okay.
It's placed in series with the appliance or circuit. If the current flowing through the circuit exceeds a safe level, maybe due to a fault or overload.
Like if that 1,000-watt iron, which should draw about 4.5 amps, suddenly tries to draw 10 amps.
Right. That excessive current flows through the fuse wire. Because of our HXI2RETE, the fuse wire heats up very quickly.
Yeah, because it has a low melting
It
point.
melts. This breaks the circuit, stopping the flow of current completely and protecting the more expensive appliance and potentially preventing a fire. You then replace the blown fuse.
So it's a sacrificial component designed to fail safely.
Precisely. A very important application of Joule's heating effect.
Okay, that covers heat. Well, what about the rate at which energy is used? We talk about watts on appliances.
That's electric power. P power is the rate at which work is done or energy is consumed. In electrical terms, power is calculated as the potential difference, V times the current. So P equals VI, P VI. And using Ohm's law, VIR, we can also write it in other ways.
Yes, you can substitute. Since VIR, you can write PPIR times IR, which gives PP equals IDR. Or since IVR, you can write PP equals V times V2 all die work, which gives PAT equals V2IR. All three formulas, VITR, VTIR, calculate power.
And the unit of power is the watt, W.
Yes, named after James Watt. 1 watt means 1 joule of energy is consumed per second.
But when we get our electricity bill, it's not in joules or watts, it's in units.
Yes. The commercial unit of energy consumption. Since a joule is a very small amount of energy for practical purposes, and power is energy per time, energy is power multiplied by time.
Okay.
The commercial unit uses a larger unit of power, the kilowatt kW, which is 1,000 watts, and a longer unit of time, the hour. So the commercial unit of energy is the kilowatt hour, kWh. 1 kilowatt hour, and that's what people commonly call a unit on their bill.
That's right. 1 kilowatt is the energy consumed when a device with a power of 1 kilowatt runs for 1 hour, and it's equal to 3.6 million joules. Wow. So, quick myth-busting moment here. Are we paying the electric company for the electrons themselves? No, absolutely not. The electrons are already in the wires circulating. You're paying for the energy that the power company has to generate and deliver to push those electrons through your appliances, doing work, heating things up, spinning motors, lighting lamps. You pay for the energy consumed measured in kilowatt.
That's a great clarification. Let's make that concrete with the last example, 11.13. A refrigerator rated at 400 watts.
Okay, 400W, which is 0.4 kilowatters.
And it runs for 8 hours every day.
Right. So the energy it consumes per day is power x time equals 0.4 kilowatters by 8 hours equals 3.2 kilowatters.
3.2 units per day. And if we calculate for a month, say 30 days,
3.2 kilowatt times 30 days gives you 96 kilowatters for the month.
96 units. And if the cost is, say, 3 rupees per unit,
Then the cost to run just that refrigerator for the month would be 96 kilowatters times RS 3.00 kilowatters times RS 3.00 kilowatters. $0.
just like that. The physics translates directly into the cost on your bill.
It really does. Understanding power and energy consumption helps you see exactly where that money is going.
So looking back, we've covered quite a journey today,
We really have. From understanding the basic flow of charge as current,
driven by the electrical push or potential difference,
encountering the opposition, the resistance, governed by Ohm's law,
and seeing how that resistance depends on the material, the length, and the thickness of the conductor.
then looking at how components are connected series versus the much more common parallel arrangement,
And finally, seeing where the energy goes into heat, explained by Joule's law, and how we measure the rate of energy use as power, leading to the kilowatt-hour unit on our bills.
it's a complete picture from the fundamental push to the final cost.
What really struck me is the deliberate material choice, like using tungsten in bulbs, because it gets super hot but doesn't melt easily,
Balancing high melting point with enough resistance?
versus using nichrome in heaters, because you want high resistance for lots of heat, but also need it not to burn up.
Exactly. It's always a trade-off, optimizing for the specific job using the properties of different materials. Resistivity, melting point, resistance to oxidation.
So here's a final thought for you, our listener. Building on that idea of resistance depending on the wire itself. Yeah, consider this. You now know resistance goes up with length and down with thickness, cross-sectional area. So think about that really long, maybe quite thin extension cord you might use sometimes, perhaps running out to the garden shed or across a large room.
Compared to the short, usually much thicker internal wiring inside a high-power appliance like your kettle or microwave.
Which wire do you think is putting up more of a fight against the electricity flowing through it? Which one has higher resistance just due to its dimensions?
And how might knowing that affect how you think about using extension cords, especially for devices that draw a lot of power? It's something to think about next time you plug something in. What materials, what shapes are quietly managing or fighting the flow of electricity all around you?